As has been mentioned, I basically self-educated myself in machine learning and data science. And even though I have graduated from applied informatics program at my university, it was a long time ago, and most of the practical knowledge comes from courses, pet projects, competition, that sort of thing. And one of the things that was confusing for me was evaluation metrics. Why there are so many? What's the point? What's the difference? What do they mean? And today I'm going to try to save some of the confusion to those who are relatively new to machine learning. So, what's an evaluation metric? Just a quick recap, it's a way to quantify performance of a machine learning model. And it's basically a number that tells you if it's any good, and you can use this number to compare different models. It is not the same as loss function, although it can be the same thing, but it doesn't have to be. So basically the difference is that evaluation metric is something, loss function is something that you use while you're training your model, while you're optimizing, while evaluation metric is used on an already trained machine learning model to see the result if it's any good. And today I'm only going to focus on supervised learning metrics. We only have 40 minutes, and I'm not going to cover them all. There's a lot of them, but these I think are the main ones to know, to understand them, and I'm going to give you an idea of what they are and how they differ. We're going to start with classification metrics, and to make things a bit simpler, I'm going to start with a binary classification problem. And the first metric that you encounter on your machine learning journey if you're doing classification is, of course, accuracy. And it is a number of correct predictions out of total number of predictions. It's super easy to understand. It ranges from 0 to 100% or 0 to 1. And it's very intuitive. You can easily get it in scikit-learn for any classificator with a score method. So the score method for estimators in scikit-learn gives you an evaluation metric, and for classificators, it is accuracy. So I built some logistic regression on some test data, some sample data, and I get almost 96%. Well, this looks amazing, but it may not be that good. We don't really know, because we don't know the context. And I'm going to show you why this is not necessarily a good thing in this case. I'm going to use the same data set to build a dummy classifier. And a dummy classifier in scikit-learn is something that doesn't learn anything from the data. It follows a simple strategy. It can generate predictions uniformly at random, or it can, in my case, just predict the most frequent value or the most frequent class it has seen in the training data. And in this case, I'm going to get 94% accuracy. And this is because the data is highly class imbalanced. I made this artificial data set with 10,000 samples. And here you can see that only 95% of the examples are positive and the 5% are negative. So simply saying that everything is positive, we're going to get 95% accuracy. In this case, 94 is probably because of the way the data got split. So 96% accuracy, is it good? We don't know. Is it a good model? Is it a bad model? If we don't know what our data looks like, we cannot say if it's a good number or not. And even if it was balanced data, we wanted to improve. From just this number, we cannot know what the errors the model is making and what to do with them and how to improve. But luckily, there is a lot of other classification metrics that we can use and diagnostic tools, and we're going to start with confusion matrix. Confusion matrix is a table, basically a matrix, that gives you numbers of how many samples your model classified correctly for what they are and how many it mistook for something else. It's technically not a metric, it's more of a diagnostic tool, but it helps to get insight into the types of errors your model is making, and it also helps to understand other metrics that are derived from it. So that's why we're going to look at it. Here's another example. I built a basic random forest classifier and got 83% accuracy on it. So to understand what errors my model is making, I'm going to build a confusion matrix. And to do that, you can simply import confusion matrix from scikit-learn.matrix. And a convention is that first you pass the actual values to a metric, and then you pass the predictions. And you get this beautiful array, which if you haven't seen a confusion matrix before, can leave you confused. And to understand this better, typically confusion matrices are also represented as tables, just like this one, for example. So by convention, on the rows you get the actual values, and in the columns you get the predicted values. This is the convention that is used in scikit-learn and, for example, in TensorFlow, but be careful because other tools may be using a different convention, and it's going to be the other way around. So even, for example, a Wikipedia page has it the other way around. So sometimes tutorials or articles on this can be misleading, and you need to pay attention to what's where. So we can learn a lot from this matrix. For example, on diagonal, we have the true negatives and true positives. True negatives are the values that were predicted negative and they were negative, and, well, true positives is when it was predicted positive and it was positive. We also get false negatives, false positives, and by summing up the true negatives and true positives and dividing by the total number of predictions, we can get the accuracy, but I wouldn't be showing the confusion matrix just to show another way to get the accuracy. There are other metrics that we can get from it. Let's say we're building a spam filter or a recommendation system, something for a user where if we say that this is something that you want and they don't really want it, they're going to be super annoying. If we see something, or if we put some important email in the spam folder and it's not a spam, again, users will be really pissed. So we don't want that. So we care about false positives. We don't want to say that this is the thing that you want when it's not. And in this case, one metric that it was going to be helpful for us is precision. Precision is calculated by dividing true positives by the sum of true positives and false positives. So if we don't have any false positives, this is going to be 1. And if we had some false positives and then we manage to reduce their number, we're going to improve the metric, and it's going to be a bit closer to 1. Now, another case is, for example, if we do something with medical diagnosis, and we don't want to send people home saying that they don't have a disease, but they do actually. In this case, we're caring more about false negatives. And in this case, we need recall. And it's very similar to precision, but in this case, we care about false negatives and about having as little of them as possible. And there is another way of summarizing the confusion matrix in one number, taking into account both precision and recall, and it's F1 score, which is just a harmonic mean of the two. So depending on your business problem, you might want to care not so much about accuracy, but not only about accuracy, but also about precision if you want to minimize false positives, or recall if you want to minimize false negatives. And these are actually, unlike confusion matrix, these are actually numbers which you can compare. And you can get them easily from scikit-learn.matrix, the same way as we got the confusion matrix by passing the actuals and the predictions. And we can use them, for example, in grid search. If we want to choose a model that gives us better recall, we're going to put the scoring parameter recall. And in this case, it's going to get us the estimator that's going to give us the best recall among the possible versions of hyperparameters. Another way to summarize a confusion matrix is called Matthews correlation coefficient. And what's important to notice about this formula is that it takes into account all 4 cells of the confusion matrix. And this is important because it gives it makes it different from F1 score and has some nice properties. I'm going to show you with examples. So let's say we have this data, we have 100 of samples, 95 of them are positive, 5 are negative, and we're just going to use a dummy classifier, so we get 95% accuracy on this. Now, we're going to calculate F1 score, and it's going to be even better than accuracy. It's going to be 0.97. And then MCC is going to be undefined. Scikit-learn is going to return 0 and give you a huge red warning because you're dividing by 0. And this is good because this is the only metric so far that gave you any red flag, any indication that something fishy is going on with your model. And it is because it's a dummy classifier. There's nothing good about it. Now, another example. Let's say we have the same data, but now we managed to classify one negative, so it's a little bit better. We get a F1 score of 0.9452. We get MCC of 0.135. But what we're going to do, we're going to say, OK, now what we called positive, we're going to call negative. The data is the same. It's just the way we say, like, this is a positive class, this is a negative class. We're going to use the same model, and we're basically just flipping the confusion matrix. Everything's the same, but F1 score changes for this model, and MCC doesn't. And this is precisely because F1 score takes into account true positives, false positives, and false negatives, and does not care about true negatives. So F1 score is very sensitive to what you call a positive class and what you call a negative class, while MCC is not. So far, and I feel that if you want to summarize a confusion matrix in one number for a binary problem, MCC gives you a better feeling of what's going on. But unfortunately, there's, of course, a downside. It doesn't really extend that well into a multi-class problem. And so far, we've looked only on the metrics that take into account whether a prediction was correct or not. But a lot of classifiers, they generate probabilities of an example belonging to one class or the other. And there are, of course, metrics that take that into account. For example, one of the popular metrics is ROC curve, which stands for a receiver operating characteristic. And to be honest, this is one of those cases where knowing what the abbreviation stands for doesn't really help a normal person to understand what it is. And this is basically a plot where you have a false positive rate on the x and true positive rate on the y-axis. And why is it a line? Why is it a curve? Why is it not a dot? And this is where the probability thresholds come to play. When we have a probability generated of an example belonging to one class or the other, it's by default is 50%. There's a decision threshold where we decide, okay, if the probability is larger than 50%, then we're going to say it's a positive class. And you can actually change this threshold. You can move it around. You can say, okay, we are only going to say that it's a positive class if the probability is higher than 60, 70, 80. And if you move, you're going to, this threshold number of true positives and true negatives is going to change, because if something was classified as positive with 60% probability, and it was, if you move the threshold to 80%, it's going to be misclassified as false negative. So that's exactly what's going on here. We're going to be moving the threshold, and we're going to be, at each threshold, calculating the true positive rate for the model and the false positive rate, and we're going to apply it as a dot and then connect them with a curve. And the next question is if it's a good curve or a bad curve. And to me, it was helpful to think of the best case scenario, the ideal unicorn sort of model that can perfectly split the two classes without making any mistakes. And in this case, the true positive rate for such a model will be 1, and the false positive rate will be 0, because we're not going to have any false negatives. And in this case, we're not going to have any false positives. So, and when we move threshold one way, we're going to be really close to this upper border of this graph. And then changing the threshold in the other way, we're going to be moving this way. So it's going to be really, really hugging that corner. And what we want our model to have is the curve really, really tightly close to that corner. But then again, it's a plot. It's difficult to compare automatically without looking at models based on the plot. That's why there is a metric called area under the curve, which basically just calculates the percentage of this plot that's under this curve. When you understand what the curve means and what it does, it's a lot easier to understand this metric. But this is not the only curve that you can use. There is also a precision recall curve, which is, follows exactly the same principle, where you move the threshold and then you plot precision and recall in this case, and then you get a curve and you can calculate the area under it. Again, why there is one curve, why there's another curve. In this case, again, it makes sense to look at the data and see if you have a class imbalance data set. I'm going to use I'll be using exactly the same example. I'm going to get the probabilities and plot the curves. And as you can see, for a class imbalance data set, ROC gives 92, and for the precision recall, it's only 57, almost 58. So again, this a lot depends on what kind of data you're dealing with. There's also log loss as another way of assessing the performance of a machine learning model that generates probabilities of as well as predictions. And it also often used as a loss function, of course, and it takes into account uncertainty of model predictions. Here you have y for, in binary case, is going to be for the true labels if it's a 0, 1, and the logarithm of probability. The minus sign before the formula is to make it a positive number, because logarithm of something smaller than 1 is going to be negative, so it's going to be difficult to compare models with negative numbers. And intuition for log loss is easier to plot than to explain with some words. So if you have a prediction that is, if you have a true label of 1 and predicted probability of class belonging to 1, you're going to have a very small log loss, but the more wrong your predictions are, the more confident your model is in wrong predictions, the log loss is going to skyrocket. So you would care about log loss when you not only care about the accuracy of your predictions, but also about how confident your model is in the predictions it makes. So we've talked about some metrics for binary problems, and let's see how they can be extended to multi-class classification problems. And you can plot a confusion matrix for a multi-class problem. In this case, it's the digits data set, so numbers 0 to 9, actually the handwritten classes, numbers and the classes that they represent. So you're going to have the same story with a true label on in the rows, predicted in the columns. The diagonal is going to be representing the correctly classified examples, but then you can actually diagnose and see like that there's 8 is mistaken for 1, or there's 2 that's mistaken for 3 for some reason, and you can make some adjustments based on what you know about the data. In some cases, something will be expected. In some cases, you can see indication of something's really going wrong with the model. You can also get precision recall and F1 score, but for a multi-class problem, the notions of true positive, true negative, and so on don't really apply directly, but these metrics can actually be extended to a multi-class problem by calculating them per label and then averaging them. And there are more than 3 ways of averaging, but I find that the more commonly used are the macro averaging, micro averaging, and weighted averaging. I'm going to show an example of how they're calculated for precision for instance, because the other metrics use the same way of, the same principle, how the average is calculated. So we're going to take this to our example, and we're going to make a confusion matrix, and then we're going to calculate each metric for each label, for each class. I'm going to say we're going to treat them as one versus all problem, meaning that if it's, for example, for a bird that we're going to calculate the true positives for a bird. It's going to be this cell. This is where we said it was a bird, and it was a bird. That false positives are going to be where we said it was a bird, so we predicted it was a bird. So this column right under, but it was not. We're going to sum these up, and this will be false negatives where it was actually a bird, but we said there wasn't. So we're going to do this the same thing for all classes, and we're going to calculate the totals as well. Now, to get the macro, and weighted average, which is going to add the number of samples here as a column, and micro precision is going to be calculated by just using the total numbers. In this manner, every sample equally contributes to the average, and they equally represent, each sample is equally represented in the average. And then for a macro precision, we're going to calculate the precision per class. Just, for example, for a bird, it's going to be 1 divided by 1 plus 1. It's 1. For cat, 4 divided by 4 plus 1 is 0.8. And we're just going to take the average of that column. And this way, every class, regardless of its size, is going to contribute equally to macro precision. And weighted precision is similar. We're going to, again, take precision calculated per class, but then we're going to weight it by the number of samples about how they are represented in the data. So just micro average, like I said before, it allows you to make sure that all samples equally contribute to the average. And macro average allows all classes to equally contribute to the average, while weighted average weights each class's contribution to the average. And when would you want what? Well, that largely depends on your data, and again, a bit on the business problem. If you have class imbalance data and you have one class that is underrepresented, but you really want to get this one right, you maybe want to use macro average to make sure this class's contribution is amplified and it's on the same level as for other classes. Scikit-learn documentation recommends using micro average for a multi-label problem. I personally haven't done much with multi-label problems, but I'll trust them on this. And a multi-class log loss is actually a more general case of a binary log loss. And the intuition is exactly the same. And the formula looks a little bit different. It's a general case. But it's essentially the sum of, we're going to go through every sample and through every possible label, and for every time we're going to be taking y, which is whether this label is correct for this sample, a binary indicator, and we're going to multiply it by the logarithm of probability of this label being right for this sample. To me, it makes it easy to understand a metric like this to just try to code it. And in my case, I just used for loops to show, to make it more intuitive. But of course, in scikit-learn, it's done with vectorized operation. It's a little more optimized, let's say. So, but for me, it helps to understand it this way. Now, I'm going to switch to regression metrics. And I find that regression metrics are a little bit easier because you're not dealing with probabilities, and you only have a continuous value, and you're predicting a continuous value. You subtract one from the other, you get residuals. And now the question is how to evaluate a model based on all those individual residuals. And if you remember, for all classifiers, scikit-learn gives you a default evaluation metric of which is accuracy. And for regressors, this would be R squared, also called coefficient of determination. The same way as you would get accuracy with the score method, you can get the R squared with the score method for regressors. R squared shows you how well model predictions approximate the true values, and it's going to be 1 for a perfect fit, and it's going to be 0 for a dummy regressor predicting average. And why is that? So this actually stems from the formula, and at the numerator, in the numerator here we have the sum of squared residuals, so the difference between the actual and the predicted value. And then the denominator, we have the squared distance from the actual values and the mean. And if you think of it, if you have a model that just predicts the mean, the top and the bottom parts are going to be exactly the same. So this will be 1 minus 1 is going to be 0. And if your model is doing even slightly better than predicting the average, then you're going to have the shorter distance between the actual values and the predicting values compared to the distance between the actuals and the mean. And this will be somewhat closer to, the whole metric is going to be somewhat closer to 1. But you can, of course, go negative if you predict infinity for everything. Everything is going to be 1 minus infinity, and technically it can be negative. But that means that something is very, very wrong with the model. And the good thing about this metric is that it has an intuitive scale. It's kind of like accuracy, so you get the percentage value, and doesn't depend on your target units, which can be a good thing. But it also doesn't give you any information about the prediction error, how far actually your predictions are from the actuals. And there's a lot of metrics which give you exactly that, because oftentimes you care about the error that a model is making. And the most intuitive one is the mean absolute error. It's basically the average of absolute value of the residuals. And you can get it again as in scikit-learn from dot metrics. There's another way of summarizing this, getting the average of the residuals using, instead of absolute values, squared values. But then you lose the metric is now not in the units of the target value, but it's instead in the squared units of the target value. That's why more commonly you would see RMSE being used, which is basically just a root of the mean squared error. And the mean absolute error and root mean squared error have a lot in common. They range from 0 to infinity, and they have the same units as y values, so you can see the error that your model is making in the units of the target values. They don't care about the direction of the errors because of the values of residuals are either squared or taken or have the absolute value. And you want this metric to be as low as possible. But they're different, of course. And RMSE gives very relatively high weight to large errors, because the residuals are squared before contributing to the average. And this makes absolute error more robust to outliers, because because they're not squared. RMSE is often used as a loss function because it's differentiable, but for an evaluation metric, it doesn't matter this much. And there's a lot of debate, and you're going to see a lot of tutorials saying, no, you should use mean absolute error of not RMSE for evaluating your metric, because RMSE is inappropriate and it misinterprets the error. And these articles are mainly based on the paper that was published in 2005 by Wilmette and Matsura. However, a bit later in 2009, there was another paper by Chai and Draxler that argued that actually it's not the case, and then RMSE is perfectly fine metric, and in fact, sometimes can be better than the absolute error, especially if you expect the error distribution to be Gaussian, which is often the case. And it's important to know that neither of this metric is going to be good enough on a small test set when you have less than 100 examples. But in practice, most of the time, you're going to have more examples in the test set, so that's OK. And in practice, I find that RMSE is a completely fine metric to use. And if you really, really want to downplay the outliers, you can use mean absolute error to as a second metric but for most cases, RMSE seems to be doing well. And there's one version of it which also is quite often used. It's a root mean squared logarithmic error, which is very similar to RMSE, except instead of y's, you get a logarithm of y. And there's a small technicality is why there is +1. And the good thing about this metric is that it shows relative error, and this is important in cases where your targets have an exponential growth. For example, if you're predicting prices and they have a wide range, if you want to error of $5 for $50 be quite a large error, whereas you want to, if it's a $5 error on a $50,000 price, it's not a big deal. So logarithm helps you to level these things. It has an interesting side effect. It also penalizes under-predicted estimates more than over-predicted, which is also sometimes useful. So I've rushed through a lot of metrics, both for classification problems and for logarithmic problems, regression problems. And I don't expect you to fully understand them all, but what I want you to take away from this talk is that there is a reason for this variety. And there is no matrix that's going to fit all the cases. You need to get to know your data. You need to understand how many outliers do you have, if it's a class imbalance data or it's not. Without understanding your data, your metric may not make sense. And more importantly, you have to know your business problem and understand what your model should care more about, because in some cases, one metric is going to help you more to achieve your final goal. In some cases, it's going to be another. So you always need to start with knowing your data and knowing your problem. Thank you. I've put some possibly helpful links here.